So yeah, general comment on weather. I will usually be able to make it in here despite weather situations because I have a little Hyundai, but my partner has a big Dodge 1500 four-wheel something or another. But don't ever come in if you feel like it's not safe to drive, right? There's nothing going on that's that critical. If you can let me know ahead of time, that's always appreciated. But, you know, there's always allowances for weather and stuff, so don't take chances. All right, so midterm coming up on Friday, so I posted a fairly concise list of topics. This is really just kind of a hit list of what we've been doing. We've covered 3 main sections in this course so far, starting with logic and logical reasoning and proofs. So there's a lot in those 3 phrases, logic, logical reasoning, and logical proofs. But, you know, the whole idea of what a formal proof is, stating a proposition or an assumption or a hypothesis, and then working logically from there, making sure you write down things that follow from what you've already written, and getting to a conclusion, or possibly doing a proof by contradiction. So negating a conclusion, working through finding a contradiction, therefore concluding that the thing you negated must have been true actually. Truth tables, propositions, what is a proposition? Equivalence of propositions, conditionals, if-thens, biconditionals, if and only if. Fallacies, right? Fallacy of denying the hypothesis or affirming the conclusion. Quantifiers, universal quantifier, existential quantifier, rules of inference, direct reasoning, chain rule, all that sort of stuff. And of course, our pinnacle of all this, mathematical induction, okay, and everything that that entails, which is the idea of a base case. Well, it's stating a proposition, it's stating what the base case is, demonstrating the base case is true, and then showing that if your proposition is true for n, it's true for n plus 1, for any n typically bigger than or equal to the base case, and then concluding by mathematical induction that your proposition is true for all n bigger than or equal to the base case. So that's where we've spent most of our energy, was in doing those kinds of things. So you definitely want to know that. You'll see some questions on logic and proofs and induction. Set theory came next, and that's stuff that you've mostly already encountered. So it's really kind of brushing up on it. Basic set operations, union, intersection. Make sure you understand complements and complement within a set. So A take away B is a set of things in A that are not in B. So you remove things from B. There's always a question on that. Make sure you can do those. Power sets. Power set is the set of all subsets. So for any set, you can find at least one subset. The power set's the collection of all the subsets. The empty set, which is a set containing nothing, which is a set, and it has a subset, which is itself, because the empty set's part of every set. It's a subset of every set. So all of that stuff. Functions, injective, surjective, bijective. So review those. Cartesian products, summations. We touched on matrices, so everything that we did in set theory, basically. But the main points are set operations, power sets, and functions. And then number theory, the stuff we've been doing, we were doing last week and a little bit the week before. I'm not going to include cryptology on here, okay, the stuff that we started on Friday and the stuff we're finishing today. But definitely understand the division algorithm, okay, which is this theorem that you can find a unique number that anything's equivalent to modulo some fixed number n, where that thing is between 0 and n minus 1. So it's the existence of this representative modular equivalent number. So modular arithmetic, the idea that if A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D. Or A times C is congruent to B times D. You can work with the original numbers, you can work with what they're equivalent to, modulo n, and you're going to get the same place in the end. And that's what we've been doing with modular exponentiation. It's what we're going to do with crypto and so on and so forth. Showing that things work, showing things by working modulo n. So these questions we've seen prove that the product of 3 consecutive integers is something or another, modulo something, right? So break it down in cases or look at these things, modulo n and so on. Prime numbers, what is a prime? Basic facts about primes, infinite number of primes. Greatest common divisor, which is Euclidean algorithm. You had homework questions on that. We worked through those in class. Fermat's little theorem, which is about raising something to the n minus 1 modulo n, where n is prime, always gets you the same value. Modular exponentiation, where we can do repeated squaring of a base and then add up those exponents by multiplying x to the 1, x to the 2, x to the 4, x to the 8, and so on. So these things that we've done to do faster manipulation of integers, modulo something. And then just be familiar with some of the open questions. We talked about Goldbach's conjecture, which you're doing for your programming assignment. Is there an infinite number of twin primes? What else did we talk about? I mean, we touched on Fermat's last theorem, which is no longer open. It's been proven. But questions like that. And no crypto stuff. No applications. So any questions or concerns about any of that?
Will there be any programming?
No programming. Your homework questions are good places to start studying and look at the questions that weren't assigned. Some of them go pretty far afield or go off in other directions or go deeper than we have. So don't panic if you can't do every homework question in the text, right? Because some of it's just outside what we've covered. But you know, if I assign some questions on finding GCD and there's a question next to it on finding GCD, go ahead and work those out, right? If you work ones that have solutions in the back, you can test those, bless you. Or you can compare answers with friends or whatever. Or you can ask in class or outside of class.
Will we be allowed a homework calculator? Like we need to test numbers out?
Sure. Yeah, that's fine. It's going to be important that I see your work, okay, partly for the sake of calculators. So if I ask you to show, 3 to the such and such is congruent to what modulo such and such, don't just give me an answer, okay? I've got to see the work. If you get the answer right and there's no work, it's probably 0 points. If you show me your work and you get the answer wrong, it's probably 9 or 10 points out of 10. Okay, so it's all about the work. Same thing with proofs. If I ask you to prove that the square of an even number is even, right? The conclusion, therefore, the square of an even number is even, is not really worth anything, right? I've kind of told you that since I asked you to prove it. It's all about the process. It's about the steps. Okay, a big part of that is starting from the right place. If you start from the right place and you go astray, that's worth more than if you start with, the conclusion and argue logically from there, but you started with something you didn't know. So think about the process and work on these this week and come and ask questions if you're not sure how to do them. Okay, I'm more than happy to spend class time going over as much of this stuff as deeply as we want. And if everybody is sick of it, we can go over it in office hours or whatever. But I don't think anybody's going to be sick of it. All right, any other comments, concerns? There should be enough space on the test, but if you want a couple of extra sheets, that's fine. So you're allowed 4 double-sided pages of notes. That's more than you need. Okay, the actual concepts we've talked about are pretty limited in number. It's more what you're doing with those, and those are hard things to put down on notes, right? That's stuff that's wired in your brain. All right, so here's what we're talking about this morning, these three people. So this is Ralph Merkle on the left, Martin Hellman in the middle, and Whitfield Diffie on the right, looking like good 1960s, 1970s programming types. This is what people looked like back then. Ralph Merkle I've actually met. He's doing different things in life, but I met him in the 90s. He was interesting to talk to. So we're talking about public key crypto systems today. And we touched on the idea of this in Friday's class. With traditional cryptography, remember we had this notion that if you encrypt something with a password, if you have that password, you can use that to decrypt. If you know in a Caesar cipher you're going to add 17 to each letter, then you know how to decrypt an encrypted message, subtract 17 from each letter. And these are usual symmetric key ciphers. So the idea of a public key, private key pair, an asymmetric system, is that you use one password to encrypt, but knowing that password does nothing to help you decrypt. And so when you send something online to an online vendor and it's encrypted, everybody's using the same encryption key to code their information. So that's public knowledge. But if you intercept someone's encrypted message and you know how they encrypted it, you still can't decrypt it, at least today. This is one of the reasons people get very excited about things like quantum computing. Because if you have enough computing power, you may be able to figure out what the decryption password is from the encryption, and then suddenly security is gone, like in the blink of an eye. Because these public keys are well known, right? So if you know that, suddenly you can decrypt traffic. But this is an interesting question. How can you encrypt something in a way that does not tell you how to decrypt it? And it's not secrecy of algorithms, remember. The algorithms are public knowledge also. It's not being able to get this decryption password from the encryption password. So that's the idea of a public key crypto system. And the idea is pretty old. So Martin Hellman, the person in the middle, was at Stanford, and he was looking into this. He was playing around with information theory, cryptography, and he had this idea of this asymmetric key system. And he talked to his colleagues, and he was told, basically, you're wasting your time. This is impossible, right? Kind of like airplane flight is impossible because planes are too heavy. He was told there was no way to do this, but he wanted to do this because he envisioned, supposedly, the idea of things like electronic commerce, the idea of being able to send information securely from multiple sources and have it travel in a way that only the receiver can decode. So he was very interested in this, and he was working on the idea. Whitfield Diffie, on the right, he'd gotten a bachelor's in mathematics from MIT in the mid-60s, and he started traveling around the country talking to crypto researchers because he was also looking for a similar algorithm, an asymmetric key system. And he spent some time at IBM, and someone at IBM told him about Hellman and said, you know, you should talk to this person. So he went out to Stanford, and he found where Hellman lived, and he had a 30-minute appointment with him. So he knocked on the door and went in for his appointment sometime in the afternoon. They started talking, and they talked until it got to be dinner time. They had dinner together. They talked some more. He ended up leaving after 11 that night. It was just this instant bond, right? Because they had both been sort of tilting at this windmill in isolation, but they had similar ideas. So they started pooling their resources in their heads and trying to come up with some new ideas. Ralph Merkle was an undergrad at Berkeley. Okay, Berkeley's just north of Stanford. And he was looking for a cool project in a computer science security class he was taking. And he had this idea of doing this asymmetric key, and he's like, this would be fun for a quarter-length project, because they needed to have a project for this class. So he wrote up his idea. He sent it to his professor. The professor said, your idea is muddled terribly. And he said, you can't work on this. So being a good academic student, he dropped the class so he could spend the time working on this project instead. So he pursued this. In 76, he was working on a master's degree at Berkeley, and he was talking to somebody about his ideas, and somebody said, you know, there's some guys out at Berkeley, they sound just like you. So he went to Berkeley, and he met Hellman and Diffie, and he became Hellman's grad student. So that's how the three of these people came together. So later that year, 1976, Hellman published a draft of a paper describing this algorithm that lets you have this asymmetric key. And while working on this and talking to some colleagues, one of the colleagues got worried about this from a security point of view and contacted NSA, no such agency. And NSA and the government got very interested in this. And they said, you know, this is a threat to national security because people can be taking secrets that we want to know and coding them in a way that we can't read what they're saying. And so they classified encryption schemes as a munition, as an instrument of war. And if you tried to leave the country with a paper that described encryption, a bunch of mathematical formulas, right, they could say that you were exporting a munition, carrying a weapon out of the country, bringing it to another country, very severe penalties. So Hellman was contacted by the friendly government agents and was told, you can't talk about this stuff anymore. This is classified. And he said, in some form, the heck, I can't. Right, this is academic freedom, this is information, this is mathematics, right? Of course we're going to talk about it. And they told him, if you talk about it, you're going to go to jail for a really long time. So he talked to Berkeley, or talked to Stanford and their attorneys, and Stanford said, you know, if they bring charges against you, we will help you defend your case. We'll supply legal counsel, we'll go to trial with you, and so on. If you're found guilty, we can't go to jail for you. Okay, that's not going to work. And if you get fined, we can't pay your fine legally if they decide that you've done something wrong. And they talked to his students who had co-authored the paper, and the students were told, don't talk about this stuff, right? So they wanted to go to a conference to present this paper. They said, you can go to the conference, but do not talk about any of this on stage. Number one, the students were early in their career, right? So an established tenured PhD arrested for espionage because of a paper they published, that's something that he can probably weather, right? Students are at the beginning, that's kind of a career-ending thing for you to go to jail. And they weren't technically employees of the university, so the university couldn't necessarily offer them the same counsel. And the first reaction from Merkel and Diffie were, we're going to do this anyway. We don't care. They talked to their families, and the families were like, yeah, you do care. So they eventually decided, okay, we won't talk at this conference, but Hellman was going to. So he went up on stage, and government was in the back, and the press was there, and the graduate students were standing on the side of the stage while Hellman presented the paper. And nobody really knew what was going to happen. It was a bit of a showdown. People really wondered if this person was going to be arrested or worse. But he started the talk, and nothing happened. And he went through and he presented the paper's results, and nobody was arrested, and that was it. The genie was out of the bottle. And it was kind of the end of the government's monopoly on encryption. So that was in the 70s, right? 1977 was when this talk was given. And it really kind of changed the tone of research and secrecy and things like that. Anybody here remember Netscape? Right, that was a really old browser. It was free, you could download it. But when you downloaded it, you had to check a box saying that you would not export this. You were a citizen of the US, you were going to use it inside the US, and you weren't going to take it outside the US or send it to anybody outside the US. Because there were two versions of Netscape. There was one with strong encryption and one with weak encryption. And if you were in Canada, you had to use the version with weak encryption. Right? You had to be in the US and agree that you wouldn't share this with anyone outside the country to use the strong encryption. So it was still treated pretty seriously. But these have relaxed over time, right? And now we kind of take it for granted that we can use all of this crypto information. Nobody's going to look at us funny or get upset about it. But then, of course, this starts to come back in the news with things like San Bernardino when they wanted to get into this person's iPhone, and Apple didn't want to help them break the encryption on it, which turned out to be easy to break apparently. But it's an ongoing controversy. It's an ongoing tension between the government and the public into how to deal with secrecy, right? Because government likes having secrets, but they like knowing other people's secrets. So let's see how to do this. And this is going to be a pretty rapid discussion of RSA. So that's a public key crypto system. Rivest, Shamir, and Ottelman are the three people. There's the three of them. And this is the system that sort of became most popular for a while. So I'm not going to hold you responsible for the details of this, but I just want to kind of run through a description of how this works, just to let you kind of see how some of the different pieces that we've been working with in this section relate to actual application, in this case, public key crypto systems. So the whole system is based on the idea of prime numbers. So let P comma Q be two large prime numbers. And the idea of large here is critical because the secrecy of RSA basically boils down to the fact that if you multiply P and Q, that's an easy operation to do. But if you start with the product of P and Q, it's hard to go from that product back to figuring out what P and Q are. So multiplication is easy, factoring is hard. And if you pick small primes, you say, okay, P times Q is 21. It's not too hard to say, oh, your primes must have been 3 and 7. Okay, so that's not a very secure pair of primes. But if your primes are 100 digits each, and your product is 200 digits, and you're trying to factor it, you're trying to find something that divides a 200-digit number, really there aren't a whole lot of things we can do other than brute force. And it's a computationally expensive operation. All right, so let P and Q be two large prime numbers, and let N be their product. And let E be relatively prime to the following, P minus 1 times Q minus 1. So E is some integer that's relatively prime to that product. So your encryption key is N comma E. It's a pair of integers, the product of P and Q, and then something relatively prime to P minus 1, Q minus 1. And again, the security of this is based on the idea that knowing these things doesn't help you figure out what P and Q are. Okay, so take your message. So code your message. And I'm going to use a simplified version here, but we could use ASCII code values or whatever we want. But let's just use a 2-digit integer for each letter, and let's just use uppercase letters, no punctuation, nothing else. So let's make A equal to 0, 0, B equal to 0, 1, Z equal to 25. So write your message. As a string of digits. So just take each letter, replace it with 2 digits, and write it out as a big, long string of digits. And then we need to break it into a block. So we're going to break it into chunks of 2n digits. Okay, n is going to be a fixed number. So if n is 15, we're going to break it into blocks of 30 digits, corresponding to 15 letters of your message. Okay, the way we pick n we want n to be a number such that this number right, 25 written out n times is less than the product of our primes. So we're just breaking our message up into blocks so that the largest possible number corresponding to a block of letters is smaller than n, the product of p and q. Okay, you could make it a lot smaller, but ideally you want to make it as big as possible, but guarantee that, you know, your largest message, which would just be a bunch of z's, is still not bigger than n. Okay, so that's how we pick this number, big N, number of letters in a block. All right. So how do we encrypt? Given P and Q, well, let me tell you encrypt first. So encryption, your ciphertext is just your message M raised to the E modulo N. So M's your message is this number corresponding to the coding of those N characters. So that's a number, raise it to the power E, modulo N, that's your encrypted message. And we can do this using modular exponentiation, and it's pretty painless computationally. All right, so that's our encrypted message. Our ciphertext is C. All right, so given P and Q, find a D such that D times E is congruent to 1 modulo P minus 1 times Q minus 1. So we know what the primes are because we created the encryption key. So we know what P minus 1 and Q minus 1 are. And so we can find a number D such that D times E is congruent to 1 mod P minus 1 times Q minus 1. And that's not too hard to do. All right, so D is what we're going to use to decrypt a crypted message. And unless you know P and Q, presumably there's no way to figure out what D is, right? Because we don't know what P minus 1 and Q minus 1 are, because we don't know P and Q. But if we know D, we can use D to decrypt our message. And all we're going to have to do is take your crypted message, raise it to the D, modulo P times Q, right, modulo N. That's going to give us our original message back. So C raised to the D will be congruent to your original message, modulo N. And again, with modular exponentiation, we can take your message, we can raise it to the D, keep reducing it mod N, that gives us your original message. Okay, so how does this work? So remember, say again?
Maybe you choose the small primes and call it 1.
Yeah.
7, 13, or something.
Yeah, I want to do it in general though, because the specifics will hide the actual process. But you can do this with small numbers and actually encrypt something and decrypt something. And I think the book might do that. Okay, so that's our ciphertext, and we know that D times E is congruent to 1 modulo n, where n equals P times Q. All right. So D times E is congruent to 1 modulo n. I wrote that wrong. D times E is congruent to 1 modulo P minus 1 times Q minus 1. All right, so what does it mean if something's congruent to 1 modulo this thing? It means it's one more than a multiple of this moduli, right? So there exists a k, which is an integer. Everything's going to be an integer, such that DE equals 1 plus k times P minus 1 times Q minus 1. That's just the definition of congruence modulo 1, or congruence to 1. So C to the D is congruent to, well, C is m to the E. So it's m to the E raised to the D, which law of exponents is just m raised to the D times E, which is just m raised to the 1 plus k times P minus 1 times Q minus 1. So all we've done is a bunch of substitution so far. And we want to do all of this modulo n. But these are actually equalities. Well, if this is congruent to this modulo P times Q, it means the difference of this and this is divisible by P times Q, which means in particular that difference is divisible by P, and that difference is also divisible by Q. That's just definition of divisibility. So C to the D is congruent to m raised to the 1 plus k times P minus 1 times Q minus 1 modulo P. And it's also congruent to that modulo Q. So assume that the greatest common divisor of m and p is 1. And that's almost always going to be the case, because p and q are prime. The only way that this would not have a greatest common divisor of 1 is if m happens to be a multiple of p. And that's very unlikely to happen. If it does, you can throw in an extra character or something, put a space in somewhere or something, right? But this is almost never going to happen. Because p is a really big prime, the chance that you would actually be crypting a block of text that translates into that exact prime, right? So this is a pretty safe assumption, and if it doesn't happen, we could just use a smaller block size or something. So given that the GCD of m and p is 1, we can use Fermat's little theorem, which says m to the p minus 1 is congruent to 1 modulo p. And also m to the q minus 1 is congruent to 1 modulo q. So now we can take this expression for c raised to the d. Well, m to the something plus something is just m to that first thing. times m to the second thing, right? And m to the first is just m. Well, exponents, we can break up this product of exponents and write this as m to the p minus 1 raised to the k times q minus 1. Right, and we're working mod p here. And we know that m to the p minus 1 is congruent to 1 mod p. So this is m times 1 raised to the k times q minus 1, which is just m. So c to the d is congruent to m mod p, and symmetrically, c to the d will be congruent to m modulo q. And the greatest common divisor of p and q is 1, because they're primes and they're different primes. And so the Chinese remainder theorem, which we mentioned but didn't go into the details of, tells us that c to the d is actually congruent to m modulo p times q, which is modulo n. And remember, we picked this number m such that m would be less than n, right? Because the largest m could be is if it was a message with a bunch of z's, which would code as n25s, and we picked our block size so that that large number would still be less than n. So if we take our crypted message, raise it to the d, and reduce it modulo p times q to a number between 0 and p times q minus 1, right? That's going to be our original message. So that's how we get our original text back from our ciphertext C. So to use this is very straightforward, right? You take two large primes, multiply them, pick a number that's relatively prime to the product of p and q minus 1, and then that encryption key along with the number n is your pair that you use for crypting. To create your ciphertext, take your message, just raise it to the e modulo n. And then take that ciphertext and to decrypt, right, you find your decryption key once. It's the inverse of e mod p minus 1 q minus 1. Just raise your ciphertext to that mod n. That's your original message. And this is all just demonstration as to why that gets you back to your original text. But to actually apply this algorithm, right, pretty straightforward. But lots of, raising things to really big powers, right? So D is a big number on order of however big E is, right, which is on the order of P times Q. So think, 100-digit primes and multiplying those out.
How do you reverse the mod P Q?
Oh, where, like here?
Yeah, how do you get 10 maths into M?
If you take C and raise it to the D, right, mod P times Q, that'll give you your original message.
So I bet you had you deconstructed the message mod PQ and
So you encrypt your message by, I don't think we can actually do this all the way, but let's try this. So P equals 5, Q equals 7. All right, so our encryption key, so we need some pick E relatively prime to 4 times 6 is 24. And E does not have to be prime, right? It could be anything relatively prime to this. So I don't know, let's pick E equal to 25. Could be anything. So our encryption would be 35, 25. This is N, this is E. And then our decryption key is a number D such that D times E is congruent to 1 mod 24. So this might be a really bad choice because it looks like a D equals 1 would get us there. So I don't know, let's make it more interesting. So what's relatively prime to 24? 4 times 6, 2 times 6. Having trouble thinking of integers. I don't know, I'll just pick a prime. So pick D such that 17D is congruent to 1 modulo 24. So find some number that makes that work. Right, and that's guaranteed because this is relatively prime to 24. So let's take your message high. So H is 0, 7, I is 0, 8. So our message M is 807. Right, there's a leading 0, we don't care about that. So to encrypt it, we just take 807, we raise it to the power E, so 807 to the 17th, modulo 35. So find what 807 is congruent to mod 35, find the square, 4th, 8th, and 16th powers, multiply the 16th and 1st powers. That gives you this to the 17th, and you get some number between 0 and 34. Okay, that's your crypted message.
Now that you have the number between 0 and 24, how in the world do we know how to get back to 807 to the power 17?
So you raise it to whatever power you got for D here, and reduce that modulo 35. Huh, why does that get you? Oh, I didn't pick a good N. Yeah, our primes are way too small. So I can only encrypt a single digit because 2525 is bigger than that. So, but let's just run with it. Let's just encrypt the message H. So H is 0, 7, so that's 7. So our ciphertext is 7 to the 17th, mod 35. H is 7, I was 8, because we start from 0. Yeah. So do that, raise that to that exponent, right, and reduce it mod 35. And then take that and raise it to whatever that power of D was, mod 35. And you'll presumably get back to a 7.
That's why you have to have it be less than.
Yeah, that's why you have to have it be less than what that product is. So you can try this at home. You gotta find that encryption key, but do a few multiplications, you'll get there.
So is it possible then, if you have the encryption key, to make a decryption key easily?
Yes, if you know how to encrypt, I mean, if you have the original primes, yes. But if all you know is that you're encrypting with a 17 and that N is 35, there's no way to figure out what this D is, theoretically. Right, because we have to work mod 24, which was P minus 1 times Q minus 1. And unless you can factor that 35. But like I say, quantum computing and some of these other things that are being developed, that presumably can do massive numbers of parallel operations might make things like factoring numbers into primes very, very tractable. And if you can do that, right, then this falls apart really quickly. So try this if you want. Go ahead and encrypt H, see what you get. Like I say, you're not going to see this on a test or a homework or anything, but it's probably fun to try at least once. So I'll try that tonight. All right, so tomorrow we will start talking about counting and combinations and permutations and see where that takes us.